So, we just did this little example where we calculated the determinant of a matrix that was capital X1, and we got capital X1 by replacing the first column of the identity matrix with X1 through Xn, and then we calculated the determinant, we got X1. Yes? Okay. That seems super duper useless, yeah?
No.
It should seem super duper useless. So, there's a cool thing called Cramer's rule, which is an interesting fact, essentially. It's an interesting way to solve the equation AX equals B. You guys with me? Okay, so here's the kind of thing that I need to figure out. If I multiply the matrix A by the matrix X1, what do I get?
Well, what's the size of A?
Well, A's
This is able to be
n by n.
n by n.
It's going to have to be square. No. Oh. Rose. I see the skateboard. I do. It's not a concern. No, be quiet. Good girl. Good quiet. Rosie's very upset by the concept that you could solve an equation using determinants. So that's going to be my plan here. Rosie, would you quit?
He's gone.
What are you barking at now? Come here. It's okay. You're fine. You're fine. He's gone. I know, the concept of determinants solving equations is very terrifying. But you're not helping. Okay, so, my goal is to solve this equation, yes?
Yes. Yep.
Okay, so what do I get if I multiply my A matrix by the matrix X1? So I'm going to assume that I have an n by n A matrix. That means that X is going to be a how big vector?
N by 1.
N by 1. And B is going to be
N by 1.
also n by 1. Are you with me on this? Okay, so I'm going to take my matrix X1, which is BT dubs. How big?
N by n.
Also n by n. Are you protesting by chewing on a rock? So, when I do this multiplication, what do I get?
The columns of x multiplied by the rows of A.
Good. No. Easier. So, I'm going to get a new matrix, right?
Oh!
And that matrix is going to have A done to the first column of X1. What's the
Yes.
first column of X1?
A bunch of x's.
Yeah. A bunch of X's, right? So I'm going to have A done to X there.
Next.
And then the next thing I'm going to have is A1, 2. Because that's going to be A done to the this column of the identity matrix, right? You see that?
Oh, and then the rest is just going to be the columns of
So
A.
I'm really just going to be filling out A13, A14, all the way until I get to A1n in the first row, right?
Yeah.
And then what's my second row going to be? Yeah, same deal, but with A2s. So A22, A23, A24, till I get to A2n. Well, that's kind of bloody weird, right?
Oh, yeah.
I'm going to pretend that AX is something. What's AX supposed to be?
B?
Yeah, AX is supposed to be B, right?
Yeah.
So I get this weird-ass matrix where it's like B1, B2 through Bn. You see what just happened there? I replaced the first column of A with the vector b, and otherwise this is just the matrix A again. You guys see that? I'm going to call this thing B1. So in the same way that my identity matrix, right? Up here I replaced the first column and I made x1. I'm doing that exact same thing here, except I'm replacing a column of A with the vector B. Hang on. Rosie's chewing on a rock because she doesn't understand where the concept of a determinant is going to come into play here. So, do you guys see where the concept of a determinant is going to come into play here?
Well, we know that since the determinant, we could take the determinant of B1, but we realize that it's A
Okay.
times X.
Good. So let's take the determinant of B1. That's the same thing as the determinant of A x1, right? Because those are the same matrix.
Yes. Yeah.
And then what was the thing you guys wanted to be true about determinants that I gave you the other day?
Split them.
Yeah, remember you can split determinants by a cross multiplication, which is super, super weird. So you can rewrite this thing as the determinant of A times the determinant of x1.
Yeah.
But what was the determinant of x1?
X1.
It's right over there. It's just x1. Okay, weird idea. So x1 then is the determinant of b1 divided by the determinant of A. You guys see that? And what's really cool is none of this particularly depended on me doing x1. You guys see that? So if I was to do this kind of over again, right? I could do this for x2. You guys see that? And then I could do it for x3. And in fact, we could do this kind of for x whatever.
Yeah.
You guys see that? So we could say, all right, look, if you have ax equals b and you want to solve this thing has a solution. I don't think we need to do that. It's okay. Okay. No, miss. Rosie, you're killing me with this bark. Hey. Come here. Give me your paws. Give me your paws. Good girl. Calm down. It's okay. Hey. This has a solution xj, right? And where am I going to get the xj's? When I need to do the determinant. Yep. We're going to do the matrix Bj, where we replace the jth column of A with our vector B that we're trying to solve for. And then we're going to divide by what? Perfect. The determinant of our regular matrix A. And I suppose I should say that Ax equals B has a solution with coordinates. Xj are these? You guys see that? Okay. So, this is kind of the flavor of how Cramer's rule works. You can use it to calculate a solution, right, to a matrix equation using kind of just determinants of matrices that you can make pretty easily. This is a nice trick sometimes. This can speed up computer solving a little bit. Solving for and, like, you guys might notice, like, the determinant of A can't be 0 for me to do this, right?
Yeah.
And so you're like, this seems like kind of a stupid trick because A is invertible, right? Well, if A is invertible, then you can just say that X is A inverse times B, right? Okay, so the deal is that if you have an absolutely enormous matrix, calculating its inverse is just such an incredible pain in the ass. that it's actually faster to do some kind of determinants, so long as things are of sufficiently convenient forms. It's not always true, it's just kind of a sometimes. Which is one of the reasons that Cramer's rule is one of these things that we talk about a bit here. It gets some use in stats. There's some kind of heavy stats time that this gets. It's not the kind of thing that you're going to see used on a daily basis to speed up computation. Things have to be of a slightly special form for this to be fast.
It's kind of the limit for like calculators and computers to calculate numbers. With this, at that point, this would make use.
Oh, so for instance, calculating the determinant at the 6x6 matrix level, it's significantly faster to reduce to lower triangular and then multiply the pivots than it is to use the cofactor form. This one is less quickly usable, but it does eventually come. It gets really easy if you have a matrix that has lots of zeros in it for some reason, because then calculating the determinant is pretty fast. Rosie, would you stop? Questions? Okay. Rosie, stop. Oh, good. I didn't actually get it off.
Okay.
What's your question?
So I know you mentioned last time that determinants are really hard for computers to calculate because they take.
Yeah, they're factorial time.
Yeah. So how would this speed up computation?
So determinants are hard to calculate using the cofactor formula.
Okay.
Using the reduce to lower triangular and then multiply the pivots is quite a bit faster.
Okay.
Does that make sense?
Yeah.
So you can get, let's see, it's not quite linear time, it's a bit higher, and I haven't looked at it for a little bit, so I'm probably lying. But everything is faster than factorial time.
Okay.
Factorial time is so bad. It might be square time. Oh yeah, it's got to be at least square time. Do you guys know what I mean by that?
Yeah.
I mean that if you double the size of the matrix, it'll take a factor of 4 longer to calculate. That would be square time. Factorial time is absolutely terrible. All right. Yeah.